Today's session I'm going to solve few problems which use Fermat's theorem, and then we'll look at the application of Wilson's theorem. Okay. First problem. Derive that a power 21 is congruent to a mod 15 for all a. From Fermat's theorem, we know a power 5 is congruent to a mod 5, right? And we know a power 3 is congruent to a mod 3, right? So now I want a power 21. So for that sake, what I do is I'll take a power 3 whole power 7, right? A power 3 is congruent to a mod 3. So I can write this as a power 7 mod 3. So that a power 21 is congruent to a power 7 mod 3. Now this a power 7 I can write as a power 3 power 2 into a mod 3, right? Same as writing a power 21 is congruent to a power 3 is congruent to a mod 3. So this is a square into a, that becomes again a power 3, that is congruent to a mod 3. Therefore I can directly write a power 21 is congruent to a mod 3. Okay. Similarly, a power 21 I can write it as a power 5 to the power 4 into a, right? This is a power 5 is congruent to a mod 5. A power 5 is congruent to a mod 5. So this is congruent to a mod 5. Then it is again a power 4 into a. So in total they are congruent to a power 5 mod 5, which is nothing but a mod 5. Hope you got it. Okay. So I can write a power 21 is congruent to a mod 5. Now when you look at this 3 and 5, they are primes and their GCD is 0. So that product divides a power 21 minus a. If you want, you can write GCD of 5 and 3 is 0. So 5 into 3 must divide a power 21 minus a. So 15 divides a power 21 minus a. Therefore I can write a power 21 is congruent to a mod 15. Okay, hence the proof. Let us look at the second problem. It says, from the Fermat's theorem, deduce that for any integer n greater than or equal to 0, prove that 13 divides 11 power 12n plus 6 plus 1. For any n greater than or equal to 0, prove that 11 power 12 plus 6 plus 1 is divisible by 13. Okay. See here, a is 11. Let me take p as 13. Okay. And you can observe that p does not divides a, right? Therefore you can apply Fermat's theorem. By applying Fermat's theorem, 11 power a power p minus 1 is congruent to 1 mod p. So a power 13 minus 1 is congruent to 1 mod 13. That is a power 12 is congruent to 1 mod 13. Then a power 12 is congruent to 1 mod 13. So I can write a power 12 to the power n is congruent to 1 power n mod 13, which is same as writing 11 power 12 n is congruent to 1 mod 13. This is same as writing 11 power 12 n minus 1 is congruent to 0 mod 13. Okay. Now this is right. I can write it as I can apply a square minus b square for this. Okay. I can split it as 11 power 6n minus 1 into 11 power 6n plus 1, which is congruent to 0 mod 13. I hope you understood. A square minus b square. A square I am writing it as 11 power 6n to the power 2. 1 power 2. So a is 11 power 6n. Okay. Since you can observe that 13 is prime, and just like how we applied in the proof, same thing. 13 is a prime and it has no zero divisors. There are no zero divisors. Mod 13. Okay, when you take modulo 13 for this, it has got no zero divisors. Therefore, I can just say this is either congruent to 0 mod 13 or this is congruent to 0 mod 13. Okay. Either 11 power 6n minus 1 is congruent to 0 mod 13 or 11 power 6n plus 1 is congruent to 0 mod 13. That is same as writing 11 power 6n is congruent to either 11 power 6n is congruent to 1 mod 13 or 11 power 6n is congruent to minus 1 mod 13. Observe one thing. When we have taken the powers for any k, that should lie in between 2, 3 up to p minus 1, right? And among this, p minus 1 is the smallest positive power of k. Okay, that is congruent to 1 mod p. That is congruent to 1 mod p. Okay, this we have applied, we observed in the proof. So it has to be the smallest positive power p minus 1. So when I take that, it should give me to 1 mod p. So when that is the case, I can omit this, right? So this is not possible, only this is possible. Therefore, I can write 11 power 6n is congruent to minus 1 mod 13. Okay, then I'll take up this 11 power 12n minus 1 is congruent to 0 mod 13. I'm taking that and I'll write this as 11 power 12n minus 1 multiply this 11 power 6 congruent to 0 into 11 power 6 mod 13. Okay, so that it becomes 11 power 12n 11 power 12n, I'm sorry, into 11 power 6 minus 11 power 6 is congruent to 0 mod 13, which is same as writing 11 power 12n plus 6 minus 11 power 6 congruent to 0 mod 13, which will be, say, 11 power 6 is 6n is congruent to minus 1 mod 13. So when I take n equal to 1, then it is 11 power 6 is congruent to minus 1 mod 13. So this 11 power 6 is nothing but minus 1 mod 13. So I can write this 11 power 12n plus 6 minus, this is minus 1 mod 13, okay, 0 mod 13, so that 11 power 12n plus 6 plus 1 is congruent to 0 mod 13. That is what we have to prove. 11 power 12n plus 6 is divisible by 13. The same thing we got, 11 power 12n plus 6 plus 1 is congruent to 0 mod 13. So it means 13 divides 11 power 12n plus 6. Okay. Now let us look at the application of Wilson's theorem. I have mentioned it is applied in solving quadratic congruences. I'll take up the theorem based on that. Theorem says quadratic congruence x square plus 1 is congruent to 0 mod p, where p is odd prime. It thus has got a solution if and only if p is congruent to 1 mod 4. So let us assume that there is a solution and we'll end up saying p is congruent to 1 mod 4. Okay. Let A be any solution of this. X square plus 1 congruent to 0 mod p. Then a square plus 1 is congruent to 0 mod p, which is nothing but a square is congruent to minus 1 mod p. Because p does not divide a, I can apply Fermat's theorem. A power p minus 1 is congruent to 1 mod p. 1 is congruent to a power p minus 1 mod p. That is same as writing a square to the power p minus 1 by 2. Can write it like this, so that which is a square is congruent to minus 1 mod p. So 1 is congruent to minus 1 power p minus 1 by 2 mod p. Right? Yeah. The possibility of giving values to p cannot take 4k plus 3. See, because it is given minus 1 power p minus 1 by 2, right? So this is equal to minus 1 power 2k plus 1, which is nothing but minus 1. Right, therefore I can say possibility that p equal to 4k plus 3 for some k will not arise. Okay. So minus 1 is congruent to minus 1 mod p. If that is the case, then p divides 2 is false. This is false because it is mentioned that p is an odd prime. Therefore, the only possibility p can take is form 4k plus 1. Okay, that is same as writing p is congruent to 1 mod 4. See, it is mentioned if it's an odd prime, okay, has a solution if and only if this is true. I had taken if it has got a solution, say a, then on applying over here you are getting a square equal to minus 1 mod p. P is an odd prime and it is not dividing a, therefore I can apply Fermat's theorem and I can write it like this. Now this p minus 1, I can revert this, so this p minus 1 can be written like this. So, and this a square is congruent to minus 1 mod p, so I can write 1 is congruent to minus 1 power p minus 1 mod p. And thus I can give the values to this p. I can give only those values other than 4k plus 3. I cannot give this. This will not arise. You can check it out. If I give 4k plus 3, 4k plus 2 by 2 it will come. It's an even integer and you are getting an even number over here. Okay. I mean even powers of 1 you are getting. So that will not arise. So the only possibility is this. So when this happens, then 1 is congruent to minus 1 mod p and p divides 2 if I use this. But that is not possible because p is an odd prime. So only possibility for p is taking 4k plus 1. So p is congruent to 1 mod p. The opposite direction you have to check that if this is the case, and then this congruence has a solution. Okay, so in opposite direction, other way, I can write p minus 1 factorial as 1 into 2 into 3 like that. Say p minus 1 by 2, p plus 1 by 2 into p minus 2 into p minus 1. I can write it like this. And we know that p minus 1 is congruent to minus 1 mod p. P minus 2 is congruent to minus 2 mod p. Like that, p plus 1 is by 2 is congruent to p minus 1 by 2, minus of p minus 1 by 2 mod p. You can check it out. Okay, I'm rearranging these factors and I'm writing p minus 1 factorial as 1 into 2 into p minus 1 by 2 till here, and these are congruent to these values. So I'll write this as minus 1 into minus 2 dash 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 minus of p minus 1 by 2 mod p, which is nothing but minus 1 power 1, 2 up to p minus 1 by 2 into 1 into 2. So 1 into 2 into 3 into p minus 1 by 2 whole to the power 2 mod p. Okay, because minus 1 sign I'm taking outside. Okay, 1 into till p minus 1 by 2 once, and when I take minus 1 outside from each term of this, then I'm getting 1, 2, 3 up to p minus 1 by 2 again. So twice. Okay, now from Wilson's theorem, we write p minus 1 factorial is congruent to minus 1 mod p. Okay, so now I'm going to replace this by minus 1. So minus 1 is congruent to minus 1 power p minus 1 by 2 into p minus 1 by 2 factorial square mod p. Why? That is, see, this is 1 into 2 into 3 up to p minus 1 by 2. That is nothing but p minus 1 by 2 factorial. Okay, it is square. It's a square. Okay, p minus 1 by 2 factorial, it's square. Now if you assume that value of p is equal to 4k plus 1, then what happens to minus 1 power p minus 1 by 2? It becomes a 4k plus 1 minus 1. So 4k by 2, that is even number. So it's minus 1 power even. So that gives you the value 1. So I can write minus 1 is congruent to p minus 1 by 2 factorial, it's square mod p. Okay, this value becomes 1, therefore. Now see, this is nothing but x square. If you take this as x, then this x square, when you take it to this side, it becomes x square plus 1 is congruent to 0 mod 4. Okay, so conclusion is that the integer p minus 1 by 2 factorial satisfies the quadratic congruence, x square plus 1 congruent to 0 mod p. Okay, hence the proof. I'll just give you a small example. Okay, suppose you have value of p as 13. Okay, now p minus 1 by 2 is 6. Now 6 factorial is 720, which is congruent to 5 mod 13, right? And you can check now it is this becomes value of x, so x square plus 1, that is 5 square plus 1, which is nothing but 25 plus 1, 26. Okay, now that is congruent to 0 mod 13, right? So it satisfies, therefore you can say, quadratic congruence. If p is an odd prime, then quadratic congruence has a solution if and only if p is congruent to 1 mod 14. Okay, check it over here. Okay, let us look at the problem based on this. First problem, find the remainder when 15 factorial is divided by 17. So I'm going to apply Fermat's theorem. It says p minus 1 factorial is congruent to minus 1 mod p. I'm going to apply Wilson's theorem. Okay, so p is 17, so 16 factorial is congruent to minus 1 mod 17. Now this 16 factorial, I can write it as 16 into 15 factorial, which is congruent to minus 1 mod 17. Okay. Now this 16 again I can write 17 minus 1 into 15 factorial, which is congruent to minus mod 17. Now I'll just multiply 17 into 15 factorial minus 15 factorial congruent to minus 1 mod 17, so that this is the multiple of mod value. Therefore this is 0 mod 17, and I'm left with minus 15 factorial is congruent to minus 1 mod 17. Therefore I can write 15 factorial is congruent to 1 mod 17. Therefore the remainder when 15 factorial is divided by 17 is 1. I'll take up few more problems based on Wilson's theorem and Fermat's theorem in my next class.